So, what if you could look up an item in a massive set instantly? Like with absolutely zero chance of a collision? Or what if you could do that same check, but using just a tiny handful of bits for each item? Well, today, we're diving into two incredibly clever data structures that make this stuff possible: perfect hashing and Bloom filters. Let's get right into it. The classic problem with any standard hash table is the collision, right? Two different keys map to the same exact spot, and boom, suddenly you're stuck chaining them together or probing around for a new slot. It's fast on average for sure, but those worst case scenarios, they can really slow things down. So how do we just get rid of that problem entirely? Well, the answer comes down to making a very specific, very smart trade-off. You can either trade the flexibility of adding and removing items whenever you want for the absolute perfection of zero collisions, or you can trade a tiny bit of certainty for a massive gain in space efficiency. And these two trade-offs, they perfectly define our two contenders today. We are on a quest for what you might call the holy grail of membership checking, just being able to tell whether an item is in a set and doing it as fast as is computationally possible. I mean, this is a fundamental problem in computer science, and it has applications literally everywhere. Yeah, like we said, standard hash tables are the workhorses here, but they're not perfect. Those collisions force them to use strategies like chaining or linear probing, which just means a lookup isn't always that single, simple operation we want it to be. And it's that potential for slowdown that really opens the door for these more specialized, high-performance solutions. So let's talk about our first solution. This is the perfectionist's approach. Perfect hashing is for those situations where you absolutely demand flawless, instantaneous answers, and you're willing to set some ground rules to get them. And this right here is the core promise. For a fixed set of keys, and that is the crucial constraint, a perfect hash function guarantees that every single key maps to its very own unique slot. This gives you that incredible, instant O of 1 query time with absolutely zero collisions. So how does it actually achieve this magic? Well, the most famous method uses a really cool two-level structure. Picture this. You've got a row of mailboxes. That's our first level hash table. Now, when we add our items, let's call them letters, some might end up in the same mailbox. But here's the trick. For each mailbox that gets more than one letter, we set up a second, tiny private grid of slots inside it, perfectly sized so that every single one of those letters gets its own unique spot. This two-step process is known as the FKS algorithm, and the real magic is in that second level. By sizing that second level table to be the square of the number of items in the bucket, you create so much extra room that the chances of another collision just plummet. It becomes statistically super easy to find a hash function that maps every item to its own spot, totally collision-free. So what's the payoff for all this? You get an absolutely unbeatable O of 1 worst-case query time. The time to actually build this structure is on average linear to the number of items, which is great. And surprisingly, even with those squared size tables, the total expected space is also just linear. But it all hinges on that one huge limitation. The set of keys cannot change. It has to be static. Okay, that's great and all, but what if your data set is enormous? Or what if it's not static? This is where our second tool, the pragmatist choice, comes into play. So let's talk about the Bloom filter, which is designed for massive scale and serious efficiency. A Bloom filter is all about probability and saving a ton of space. It's a data structure that can tell you if an item is possibly in a set or if it is definitely not in a set. It pulls this off using an incredibly small amount of memory, but it comes at the cost of perfect accuracy. The best way to think of it is like this. You have a long row of light switches, and they're all initially off. To add an item, you run it through, say, k different hash functions. Each function tells you which switch to flip on. Then, to check if an item is in the set, you just run it through the same k hash functions and look at those switches. And right here, this is the Bloom filter's rock-solid guarantee. If you check the k switches for your item and even one of them is off, you know with 100% certainty that the item was never added. It's impossible for it to be in the set, because adding it would have slipped that switch on. This means zero false negatives. Ever. But what if all the switches are on? Well, then the answer is only maybe. And you might be wondering, why? Because those switches could have been flipped on by other items that were added to the filter. This is what we call a false positive. The item might be there, or you might have just gotten unlucky that other items happen to light up its exact same pattern. Now, I know what you're thinking. Maybe sounds kind of risky, right? But the beauty of a Bloom filter is that you are in complete control of the odds. See, this probability P of getting a false positive is just a function of the array size M, the number of items N, and the number of hash functions K. You can actually tune these parameters to make that error rate as vanishingly small as you need it to be. All right, so we've got two really powerful tools for fast lookups, but they operate on completely different principles. Let's put them side by side and see exactly where each one shines. This is the fundamental trade-off in a nutshell. Perfect hashing gives up the ability to change the set. It has to be static, in exchange for perfect, 100% certain answers. The Bloom filter, on the other hand, gives up that 100% certainty in exchange for these incredible savings in memory. Let's break this down a bit more. Look at the symmetry in the errors. Perfect hashing has 0 false positives, while a Bloom filter has 0 false negatives. Their query times are both super fast, but updates are a huge distinction. Perfect hashing is static, no changes allowed, while a Bloom filter can handle additions. And then there's the biggest differentiator, space. We're talking O of n times words for perfect hashing versus O of m bits for a Bloom filter. That is a massive, massive difference in memory usage. So when do you reach for perfect hashing? Well, you use it with your data is fixed, you know it all up front, and you need 100% accurate, instant answers, no exceptions. A perfect example is the set of reserved keywords in a programming language. Like if, else, for. That set is fixed, and a compiler needs to check against it millions of times with perfect accuracy and speed. And when do you use a Bloom filter? You use it when you're dealing with a massive scale, and you need to be really frugal with memory. A classic use case is a web browser, checking if a URL is on a huge list of malicious sites. The filter can live right in memory and quickly say, definitely not malicious for almost every URL. It's only for that rare maybe that the browser has to do a more expensive check, like over the network. So at the end of the day, the decision between these two amazing structures really just comes down to understanding your problem's constraints and figuring out what you're willing to trade. And I think this sums it up perfectly. It's perfection for a static world, or it's efficiency for a massive one. It's just a beautiful example of how different algorithmic solutions are tailored to solve very specific variations of a problem. So here's the core takeaway. I think of it as buy versus trade. With perfect hashing, you make a one-time investment when you build it to buy guaranteed worst-case speed forever. With a Bloom filter, you're making a continuous trade. You're spending a tiny probability of error to buy back an enormous amount of space. So as you think about the systems you work on, I'll just leave you with this question. Where is there a slow, expensive check that happens over and over again? And could a small probabilistic filter sitting in front of it save you a massive amount of time and resources? The answer just might surprise you. Thanks for joining me.